All right, so let's start off with, I guess, we'll start off with this topic covers irrational functions. Mm, I'll start off with this one. I think we did this last week, but we'll still like play around with this one a bit. So let's look at the differences between A, B, and C. The question's asking you, find the domain of a function. How would you classify these functions? What are these functions? What's A? If you had to name it, is it a quadratic? There's a quadratic in the denominator, right? But it's made up of two
Mm-hmm.
functions. There's a numerator and a denominator. This is an example of a rational function. So both of these are rational functions because you have f of x over g of x. It's in this form. You have a function on the top, and you have a function on the bottom. That's a rational function. A reciprocal function would usually, okay, usually it just has a number on the numerator. It doesn't have another function. It just has a constant. That's the difference between a rational function and a reciprocal function. The third one here, c, is just a square root function because there's no numerator denominator thing happening there. For a reciprocal function or a rational function, when the question asks you to find a domain, what you need to do is you need to check for two things. You need to check whether there's a hole in the function. And you can do this by simply simplifying the functions. To check for this, you, you just go ahead and clean it up if you can. I wrote simply there. I meant to say simplification. You just simplify it and see if things cancel out. If there's a hole, okay, there's gonna be a hole if things cancel out. For example, let's say you have x plus 2 over x squared plus 5x plus 6. How would you classify this function? Is it a quadratic? Notice there's a numerator and a denominator.
Mm-hmm.
So that's a rational function, yeah?
Yeah.
So now let's see if we can simplify this. On the top, we have a linear function, so you can't really do anything. On the bottom, we have a quadratic. What does that factor out to? You gotta man this, right? And it's pretty simple. It's gonna be x plus something and x plus something. What are the two numbers?
3 and 2.
3 and 2. So now you'll notice that x plus 2 and x plus 2 cancels out, right?
Mm-hmm.
And your final function, you're left with 1 over x plus 3. This is the simplified function. But you gotta remember that your function, you canceled out x plus 2, x plus 2. What does this mean? This means, now you look at this denominator, at x equals minus 3, you have a vertical asymptote. Whenever the denominator is set to 0 and solved, that's when you have a vertical asymptote. And you're supposed to do this after you've cleaned up your expression. So at x equals negative 3, if x were to be negative 3, you'd be dividing by 0. So at x equals negative 3, there's a vertical asymptote.
Mm-hmm.
And then we canceled out x plus 2, x plus 2. If things cancel out, there's a hole. So where is your hole? For this function, what you do is you set the canceled out term equal to 0. So here we cancel out x plus 2. We're going to set that equal to 0. So we're going to get x is equals to minus 2. That means at x equals minus 2, there is going to be a hole for this function, okay? So in terms of
Mm-hmm.
the domain for this would be x cannot be negative 3 because there's a vertical asymptote there, and x cannot take the value of negative 2 because we cancel that out and there's a hole in the curve. So that's how you do a domain for a rational function. You check for holes and then you check for vertical asymptotes by simply setting the denominator equal to 0. So using this concept, let's attack some of these problems. So again, part A, there's a linear on top. You can't really do anything with it. And on the bottom, what do we have? We have x plus 2, x minus 1. What's the domain of this function? So nothing cancels out. You can't cancel 2x plus 1 with anything. So this is
Mm-hmm.
not a whole question.
X can't be negative 2 or 1.
Yeah, and you're done. That's it. So if you want to write the domain, you're going to say XER. X cannot be negative 2 and positive 1, okay? That'll be
Mm-hmm.
the domain in the set notation. If you want the domain in the interval notation, it's going to be a little bit trickier. So in the interval, it'll look like this. From negative infinity to negative 2 exclusive, union, negative 2 to positive 1 exclusive, union, 1 to positive infinity. So that'll what it's going to be in an interval notation. You may get away with writing this. Now this is going to depend. I'll be fine with this, but this is the proper way of writing it using unions for interval notation. This
Mm-hmm.
way, I don't know is going to work or not. Would work with me, but I'm not sure about your teacher, so double check. So that's how you do interval. Let's do B. What kind of a function is it? So again, you ask yourself, there's a function in the numerator. It's a fraction. There's a function in the numerator. There's a function in the denominator. So what kind of a function is this?
Rational?
Yeah. So again, we got to do the same thing. At this point, is anything that I cancel out? You can't really simplify this. This is as far as you can go. Does anything cancel out here?
No.
No. Could I move this upstairs? So could I do x1 over 3 minus 2 and just leave a 1 in the denominator? Am I allowed to do that?
No.
No, because there's a plus 1. If there was no plus 1, you could have. So here you can't simplify this. This is as far as you can go. So that means when you're checking for the domain, you want to set the denominator equal to 0 and see what value of x would give you a 0 in the denominator. So for this, you're going to get a square root of negative 1, which doesn't exist on the real number system. So that means there's no value of x that would make this function moot. So XCR would be the answer. You get it?
Mm-hmm.
There's no value of x that you can plug in there that would make the denominator a 0. And the numerator is a odd degree index. So that means you can put in any value. But if you had, let's say in the numerator, instead of having this root 3, you just had a square root. In that case, then your function would have a restricted domain because now you can't put negative values in a square root. If that were the case, then the answer would be x has to be positive because square roots can, or any even degree index cannot take negative numbers inside of it, right?
Mm-hmm.
Okay, C. Let's look at C. 4 minus x, x squared minus 1. How do we find the domain of this? Well, let's go one by one. So let's look at this one. 4 minus x. Can x be 4? Basically, what I'm trying to see here is what value of x would make this expression negative? Because you can't have a negative inside a square root. So now I mean, if you know your transformations, you can see what this looks like. This will look like negative x plus 4. Negative x minus. It looks like this.
Mm-hmm.
That's one way of doing it. From here, you can see that the domain is x has to be less than equal to 4, right?
Mm-hmm.
That's one way of doing it. If you know your transformations, which you should know, this is very helpful. If you don't, then you just plug numbers in here. You ask yourself, can x be 4? The answer is yes. Can x be 5? Can x be 5? Or just looking at the first bracket. No, it cannot, because if x were to be 5, then you would get 4 minus 5, negative 1, right?
Mm-hmm.
So x cannot be 5. Can x be 4.1?
No.
No. So you know you have a hard limit now at a 4, right? At
Mm-hmm.
positive 4, you have a hard limit. And you know you can't take any of these values, so you're probably going this way. And then you can quickly check for other numbers here if you don't know how transformations work for the square root. And you'll see that the domain for the first function is that x has to be less than equal to positive 4. Now let's look at the second one, x squared minus 1. So again, you can also do it this way, x squared minus 1. You need this bracket to be bigger than equal to 0, right?
Mm-hmm.
You could have done it this way as well. You need 4 minus x to be bigger than equal to 0. Then 4 would be bigger than equal to x, and this is what we have here. So let's try the same approach here. X squared is greater than equal to positive 1. Now with the square root, you have to be careful because the inequality math is a little bit tricky. So what you have a function x squared. This is just the parent function. But you need these to be more than the y value of 1. Okay?
Mm-hmm.
You need it to be more than y value of 1. So now you ask yourself, it can also be exactly equal to 1 because you have this condition here, greater than equal to. So for this, let's think about it. This is just the x squared. If x is 0, y is 0, that's not greater than 1, that's out. What about 1? When x is 1, y would be 1. That's good, right? Because
Mm-hmm.
y can be exactly 1. At 2, it's 4. So anything greater than 1, you're good, okay?
Mm-hmm.
What about on the other side, negative 1? Are you good on the other side, over here? Over here, anything to the right of 1, you're good. You get positive y values. What about on this side, to the left of negative 1?
It's still positive.
It's still positive, right? So for this, you can either be greater than equal to 1, or you can be less than equal to negative 1. Do you agree?
Mm-hmm.
Under both of those conditions, for this quadratic, the y values are going to be more than 1. So now we've listed out all the conditions, the individual domains for every function in here. Now you have to do one last step, which I don't think is terribly difficult. You just have to find the intersection. So now you have multiple domains. The combined domain for the entire function. The combined domain will be the intersection of these domains. So for this guy, positive 4 here, going this way. That's for the first function. For the second function, you have, so 0 is here. So you have 1 here going this way, or you have negative 1 going this way. Now, where do these intersect? That's tricky to think about, actually. Now that I think of it, it's not as easy. But if you look at the sketch, it's pretty obvious. So again, the question is, where do the domains intersect on the number line? And I've graphed both of the domains. So here's the answer. The domain's going to intersect right here, from 1 to 4, okay? From 1 to 4, that's one answer. And on the other side, to the left of negative 1. So that'll be the combined domain. You want to see where they intersect. Cool?
Mm-hmm.
So it's a little bit difficult for sure. Because just finding the individual domains are a little bit difficult, but honestly, this part, once you draw it out, it's not terribly difficult. So that was for a square root function. This next question deals with transformations. So again, you have to see whether the transformation is being done inside the function, being done inside of the x, like this. If it's being done inside, remember, it's the x values that will change. If it's done outside, then it's the y transformation. It's the vertical transformation, and the y values will change. These are for horizontal. If it's being done inside, if it's being done outside, it's for the y values for vertical transformations. So let's look at A. If you know, you know. It's a 5-second answer. Y is equals to negative f of x. What does a negative there do? I'll tell you it's a reflection. Now the question is it going to be on the y-axis or on the x-axis? I'm going to give you the general form of transformations. This is the general form. This works for everything. If A is negative, then it's a reflection on the y-axis. If K is negative, it's a reflection on the x-axis. So this negative sign here, is it inside the function or is it outside the function?
Outside.
So is that A or K?
It's A.
It's A. So what does it do?
It's a reflection on the y-axis.
And you're done. So you can just say it's a reflection on the y-axis. Let's look at B. Same concept. The 2, is it for x or y?
It's for y. I mean x.
The 2 is for x? No, it's not. It's outside f of x. So the 2 is for y. So in part B, your A value is 2. What about this minus 1? Is that C or D?
It's c.
It's D. Actually, wait a second. It's C. It's C. It's outside of the f of x, right? It's
Mm-hmm.
outside of the f of x. Anything outside, it's going to be vertical transformations. So the 2 is a vertical stretch, okay? The 2 is a vertical stretch by a factor of 2. What about the minus 1? Does it move it left, right, or up or down?
It moves it down.
It moves it down is correct. C is negative 1. It moves it down, and you're done. Let's look at C. Okay, why don't you tell me for part C, what's A, what's K, what's D, what's C? And all you're doing is comparing this equation with this equation.
A is 1.
A is 1, yeah. So that doesn't do anything to the transformation, so you can ignore it. What about K?
K is also 1.
Yep, that doesn't do anything to the transformation, you can ignore it. What about D?
D is negative 3.
Is it
Or
negative 3 or positive 3? See
it's
if it,
positive 3 because
it's,
you moved to the right.
yeah, and then this moves it 3 units right. What about the C value?
Um, it's 2
It's 2 down, up or down?
up.
Up is right. And you're done. Cool? So that's
Mm-hmm.
transformations. It'll help you graph out functions very easily, I think, which is going to be the next question. And so without using technology, graph the following. So it's just a rough sketch, and most of these are, well, all of them are polynomial functions, so how hard could this be? What does x cubed, the parent function, look like? So x cubed looks like this. Starts in quadrant 3, ends in quadrant 1, right? So
Mm-hmm.
this looks like this. Part B, x plus 1 cubed. So the parent function is the same. It's a cubic function. What does a plus 1 do? Left, right, up, or down?
Right.
No, it moves it left. X lies, okay? So plus 1, you'd expect it to move to the right, but because the general form is like this, right? X minus d. See how it's already minus here to begin with?
Mm-hmm.
But here it's plus. So that means your d value is -1. It would move it to the left. So in
Okay.
terms of the sketch, it's going to be the same thing. The only difference is that right now it's going through the origin, okay? Over
Mm-hmm.
here, the, this is called the point of inflection. We're kind of like concave up, sorry, concave down. Right here, it's a concave down shape. And then it kind of changes it to concave up. When this happens, and this is going to happen for any odd degree polynomial except y equals x, this point right here, where it shifts direction from down to up, that's called a point of inflection. To find that, you would set the double derivative equal to 0. I can show it to you here, because this is very simple. Y equals x cubed. What's y prime? What's the derivative of this?
It's 3x squared.
It's 3x squared. We gotta go one level deeper. What's y double prime? What's the derivative of y prime?
It's 6x.
It's 6x. And now you set this equal to 0, you'll see that x is gonna be 0. That's why there was a point of inflection at the origin here. But this x plus 1, what it does is it's gonna move it 1 unit to the left. So now your point of inflection would be there. So your curve is gonna look like this. Okay?
Mm-hmm.
Okay, what about C? What does the -2 do?
Moves it to the right.
Moves it to the right. What does the +3 do?
Moves it up.
Moves it up. So I'm going to draw it here. So it moves it to the right. So this point of inflection is going to shift 2 units right, 3 units up. I'm using that as my reference point. Okay.
Mm-hmm.
So this was 0, 0. This will move it 2 units right, 3 units up. So it's going to go to 2, 3. So your point of inflection will be somewhere here. So your curve would look something like this. Cool?
Mm-hmm.
Not the best drawing, but it should look like this here. So that's cubic functions. Pretty easy to deal with. I don't think it's terribly difficult. Four minus x squared. What does this look like? I'll give you a clue. What you can do is you can rewrite that as -x squared plus 4, which is way easier to see. Nope. So first of all, -x squared, it's going to open up or down?
Down.
Down. The +4, that's your y-intercept. This is your curve, right? That's it.
Mm-hmm.
Easy peasy. Done. Y equals to root x, that's just the parent function, square root function. Goes through 1, 1, goes through 4, 2. And then if you keep going, goes through 9, 3. Okay?
Mm-hmm.
Just a square root function. Now part F. Part F is related to part E. You have a square root and you have 2 times the square root. Does this affect the y values or the x values? Is it on the outside or on the inside? That's all you have to think about.
The outside.
The outside. So it's going to affect its y
Why?
value. Just for note, okay? Just for note. If it was inside, it would affect the x values, but they would not double, they would half. Because inside it's the opposite. Remember, x lies, so anything inside the function is opposite. So if it was root 2x, your x values would be halved. For 2 root x, your y values are going to be doubled. Everything on the outside is as is. So to graph this, x values are going to stay exactly where they are. The y values are going to double. So I'm going to build it on this. 0, 0, the y value doubles, stays right there. 1, 1, the y value doubles, it's going to become 1, 2. 4, 2, the y value doubles, so at 4, it's going to be 4. Okay?
Mm-hmm.
So 2 root x looks like this. It's exactly twice as bigger on the y-axis, and that makes sense because that's what the transformation does. Okay?
Mm-hmm.
So we're done with this one, E and F, I guess. What about this one? Negative 2x. It's pretty simple. What kind of a function are we dealing with?
Exponential.
Exponential. So you know any exponential function, the parent function looks like this. This is 2 to the x, 3 to the x, e to the x, doesn't matter, 10 to the x. Everything looks exactly like this. They all go through the y value of 1. The only difference between these is that the bigger the base, the faster it would increase,
Mm-hmm.
like that. So that's the parent function. Here it's negative 2x, so is that a reflection on the x or the y?
The x.
It's a reflection on the y. Again, is it outside the function or inside the function? If you let y equals 2x, you'll see that it's negative, right? The negative is outside. Okay?
Mm-hmm.
This would be on the inside. So right now it's affecting the y values. Actually, I don't know what I'm saying. You're correct. It's going to look like this. It is a reflection on the x-axis. Flips it upside down.
Okay.
Okay, h. The plus 1, is that affecting the y values or the x values? Again, you want to think about, is it inside the function or is it outside the function?
It's affecting the x values.
So what does this look like? How would you classify this function? You just finished this chapter. That's a clue. X to the power negative 1. It's a reciprocal function, okay? X to the
Mm-hmm.
power negative 1, you can write it as 1 over x. It looks like this. There's an asymptote there, there's an asymptote there. Reciprocal functions always have two asymptotes. Not necessarily, actually. I'll take that back. It always has a horizontal asymptote, but it may not have a vertical asymptote. If you have something like this, there's no value of x that would make this 0. So this one only has a horizontal asymptote. But y equals 1 over x, that has both of these. So I can rewrite that as 1 plus 1 over x. Now, are the x values being affected or the y values being affected? It's the y, okay?
Mm-hmm.
Because you're adding 1 to whatever your previous y value was. The new y
Mm-hmm.
value will have 1 unit higher values. So you're affecting the y values. So all it's going to do, okay, look at this. All it's going to do is shift this plot 1 unit up. That's the only thing it's going to do. So right now there's a horizontal asymptote on the x-axis. What's going to happen is that this axis is going to shift 1 unit up. So maybe I'll draw a new one. So we'll go here, but the vertical asymptote stays where it is because we're not touching any of the x values. So your new plot will look something like this. It's the exact same shape. All we've done is shifted it 1 units up because that's what the transformation was. And you're done, okay? That's it.
Mm-hmm.
Easy peasy. Okay, what about this one? How'd you classify this function? It has a name. Starts with P. Notice this function, there's multiple parts to it, right? You don't just have f of x equals this or f of x equals that. You have one f of x, you have one y that can take two different equations, yeah? This is called a piecewise function. Piecewise. That's when a function is divided into multiple parts. It's not that difficult because when you actually look at the function, it's made up of a quadratic and a linear, right?
Mm-hmm.
And all it is that quadratic, this function is going to be valid or it's going to apply to the left of zero, and this function is going to apply to the right of zero. So let's look at part A. Evaluate f of negative 2. Again, it's easier than you think. F of negative 2. Do we use the top one or the bottom one for f of negative 2? So you want to see here, right? Negative 2. Does it fall under this condition or does it fall under the bottom condition? Between two of these, where's negative 2? It's going to be the top one, yeah?
Mm-hmm.
It's very simple. You just look at which equation would apply. You just look at the x value. The x value is negative 2. This is x is greater than 0, so this is not going to apply. I have to plug negative 2 in here. And it's just that easy. So it's a two-step. 1 minus negative 2 squared. 1 minus 4 is negative 3, and you're done. What about f of negative 1? Which
The,
equation would apply?
the bottom one.
The bottom one. So it's 2 times 1 plus 1, it's 3, and you're done. Easy peasy, right?
Mm-hmm.
B, sketch the graph of f. Okay, so I'm just gonna leave these values in here so we can use them. So sketch the values of f. Cool. So where you want to start off in a question like this, when there's multiple parts, is the point where they're divided, or at the point where they split up. Okay? At a point where they split up. Can you tell me what's going to be f of 0? Because the point they split up is 0. So we want to find the y value at that point. Which equation would apply at f of 0, the top or the bottom?
The top.
The top. So it's going to be 1 minus 0, it's going to be 1, correct?
Mm-hmm.
At f of 0, the y value is 1. And the top function is valid to the left of 0, to the left of x value of 0. So 1 minus x squared is the same thing as negative x squared plus 1. Looks like this. Do you agree?
Mm-hmm.
Negative x squared plus 1 is just the x squared flipped upside down and moved 1 unit up. So that means the sketch of this to the left of 0 is just going to be strictly this part. We don't care about this because this function is only valid to the left of this. So x squared minus 1 is equal to 0. We know that the x-intercept, this point, will be 1. Well, it'll be plus minus 1 if you want to go both ways. The x-intercepts for this function will be plus minus 1. But since we're only interested in the left half, we know that the x-intercept will go through negative 1. Therefore, the sketch of this, the top function, would look something like this. Now for the right function, what's gonna be f of 0 for the right function? Let's focus on this one. Does f of 0 exist for that? No, right?
Mm-hmm.
No. But you still have to find the y value. I think that's the best way to sketch it. So what I'm gonna do is I'm gonna put a closed circle here. So you know that, maybe I'll do it in red. So you know that this function, this is the y value at this point. So now what I'm going to do is I'm going to find f of 0 for the bottom function. So that's also going to be 1, right?
Mm-hmm.
That's also going to be 1. So what I'm going to do is I'm going to use an open circle to denote the bottom equation. But notice that the open circle from the bottom equation gets automatically filled by the closed circle from the top equation. So that means our y value for the combined function is going to go through the y-intercept of 1. And then for the linear function, I have another point here that we found from part A. So I'm just going to plug that in. So 1, 3. So at 1, the y value is 3. 1, 2, 3. So like that. So our bottom equation would look like this. And this doesn't have to be done in different colors. They can be done in the same color. So ultimately, your sketch would look something like this. And that's the sketch of this piecewise function. Cool? So again, you just have to know how to do it. First time it's going to be difficult, but if you just look into it, it's just a linear and a quadratic. It's a grade 10 question. The only new thing is you have to account for where the first function ends and where the second function starts. What was the name for this? Piecewise, okay? Keep that in mind. Piecewise function when there's multiple parts. This one is called a composite function. Anytime you see fog, anytime you see this symbol, you see that kind of looks like an O, but it's really
Mm-hmm.
not an O. We call these composite functions. A better way of thinking about these is that it's a function within a function, and this can go to infinite levels. Function within a function. So let's look at A. A says f composite g, like that, fog, right? F of g. You can rewrite this as f of g of x. They're equivalent. You can put this function inside of this function. For b, that's equivalent to g of f of x. For c, that's equivalent to g of g of g. So there's 3 levels there. Let's start with a. F of g of x. And again, these, once you know, they're very simple. It's just an algebra question. F of g of x. For these problems, for composite problems, you always work on the inside and you work your way outside. You're not allowed to touch the outer bits until you've cleaned up the inside. So that f on the outside is going to stay as it is. On the inside, we have the function g of x. What's g of x? Do we know what g of x is?
2x minus 3.
2x minus 3. Now, this is the trickiest part, the next step. What's going to happen now is that on the inside you have 2x minus 3, on the outside you have an f. So the solution to this will be you have to plug this as x. That's your new x into the f function. Whatever's in the bracket, you have to replace that. You have to replace x's with that. So let's do it. So it's gonna be, you have an x here, you have an x here. So it'll be 2x minus 3 squared, okay?
Mm-hmm.
Plus 2 times 2x minus 3 minus 1. And you can open this and combine the like terms if you want, but for the sake of time, I'm gonna leave it here. And that's the answer to the question. Cool?
Mm-hmm.
And if you want, it's just 10 seconds. This will be 4x squared minus 12x plus 9 plus 4x minus 7. So it'll be 4x squared minus 8x plus 2. That'll be the final answer. So that's done. Let's try doing B. Why don't you help me with B? So we know we're doing Goff, G of f of x. What's the next step? So the outside part, you're not allowed to touch it. So g stays there as it is. But on the inside, you can replace f of x with what it's actually. What is the value of f of x?
X squared plus 2x.
Yeah, so x squared plus 2x minus 1. What's the final step? What do we do with this?
You plug it into the x values for g of x.
Yes. So it'll become 2. There's only one x value for g of x, so it'll become 2 times this drops down, right?
Mm-hmm.
Minus 3. Let me plug this. Oh, why am I? You don't need a calculator for this, but you can clean this up. And that's it for that.
Mm-hmm.
Easy peasy. Part C is triple G. And again, it's not that hard. You just have to work one step at a time. Take it one day at a time. So the first thing, I'm going to replace this g of x with what it is. So you have g of 2x minus 3. What's the next step?
You plug in 2x minus 3 into g of x.
Yes. So this outside g stays on the outside g.
Mm-hmm.
So in this next step, we're going to plug 2x minus 3 into the g function. So it'll become 2 times 2x minus 3 minus 3, right? You have 2x minus 3, but now your x is this. That's why it looks like this.
Mm-hmm.
Well, let's clean it up before we plug it back in. So this becomes g, still on the outside, 4x minus 6 minus 3, so that's going to be 4x minus 9. And then for the final step, you're going to plug 4x minus 9 in here as x, because the function is still g. 2x minus 3 it is, right? 2x minus 3. So again, 2 times x minus 3, 8x minus 18 minus 3, that's 8x minus 21. Cool?
Mm-hmm.
And you're done. So again, it's just pure algebra question if you know what you're doing. And you will run into these in grade 12, I'm sure. Maybe in the first chapter of grade 12. Let's move on to one last section for the next 10 minutes. Trig. How are degrees and radians related? Do you remember what radians is? What's a radian? If I asked you what's a radian, what is it? It's just a measure of angles, okay? So
Mm-hmm.
someone asks you, what's a radian? Well, it's a measure of angles. If you want to be fancy, you can say relative to a circle because the angles are in terms of pi's. So we measure angles with relation to a circle. That's what a radian is. The question says convert from degrees to radians. And again, this is also easy if you just know the conversion factor. It's just a grade 10 level problem if you know the conversion factor. And this is the conversion factor. 180 degrees is pi, and the symbol for radians is C. You don't have to write it, but C is the symbol for radians. So 180 degrees is pi radians. Divide both sides by 180. What would 1 degree be? You have this equation. If you divide both sides by 180, what do you get on the right side? You'll get pi over 180, right?
Mm-hmm.
Pi over 180 radians. So this is your conversion factor. Oh, yeah, it's a combination of both of them. So how does that help us? Let's start with part A. 300 degrees is the question. Start with this equation. Multiply, so you have a 300 here, right? You have a 1 here, but then you have a 300 in here. Now the only thing you can make this 1 into 300 is if you multiply by 300, okay? could add 299. That's another way, but that doesn't help us on the right side, so we multiply it. So you multiply both sides of this equation by 300. Now look at this. You'll get 300 degrees on the left side. What do you get on the right side? Pi over 180 times 300. Yeah?
Mm-hmm.
Now you have to simplify this a bit as well. 6 goes into 18 and 30. That means 60 goes into 180 3 times, goes into 305 times. So the final answer is going to be 5 pi over 3 radians. So 300 degrees is 5 pi over 3 radians. Okay?
Mm-hmm.
Okay, what's the answer to B? It's the same question, right? What do we multiply both sides of this equation by?
-18.
Negative 18. So you get negative 18 degrees is pi over 180 times negative 18. Quick maths, what does that simplify to? It has to have a pi, so don't worry about plugging it in a calculator.
Do you just get a 10 in the denominator?
Yeah, so negative pi over 10. And negative as well, right? And negative because angles
Mm-hmm.
can be negative depending on your reference. We talked about this before. If you, this way is positive angles. If you go counterclockwise, it's positive. But if you go this way, that's called clockwise, then your angles are going to be negative. So negative pi over 10. Uh, so this entire thing is pi. So it's 1/10 of this. So it's probably somewhere like here. So this will be negative pi over 10. So that was going from degrees to radians. Converting from radians to degrees is just the opposite. So last time it was 100 degrees is pi radians, and then 1 degree is pi over 180. And depending on what number you have, you multiply both sides of this equation. Now it's just the orders flip. Now pi radian is 180 degrees. So that means 1 radian is 180 degrees divided by pi. So we're going to be using this, okay?
Mm-hmm.
So for part A, what do I multiply both sides of the equation by? Right now I have a 1. I need 5 pi over 6. So what do I multiply it by? 5 pi over 6, right?
Mm-hmm.
I have a 1. I need 5 pi over 6. The only way I'm going to get 5 pi over 6 from a 1 is if I multiply it by 5 pi over 6. So you do it on one side of the equation, you have to do it on the other side of the equation. You'll see that whenever you're converting to degrees, the pi will cancel out if there's a pi, like that. Then 6 goes into 180 30 times. 30 times 5 is 150. Okay?
Mm-hmm.
So therefore the answer to A is 150 degrees. There's an easier way to do it, to convert from radians to degrees, and this is the easier way. And this only works, it only works if there's a pi. If there is pi. So it's not going to work for B because B doesn't have a pi, but A does. So the way to convert from radians to degrees is you simply replace that 180. You see this pi? All you have to do is replace that pi by 180. So 5 times 180 divided by 6, like that. Goes into 30 times 150, and that's the answer in 2 steps. So you can either do it like this or do it like this. Just remember that one method, the easier method, only works if there's a pi. It's not going to work for B. Let's try doing B. And again, it's easier than you think. We're again going to start off um, right here. I'm going to start off with this equation, and then we're going to ask ourselves. So this is my conversion factor. Right now there's a 1. I need a 2 there. Last time we needed a 5 over 6. We multiplied it by 5 over 6. What do we multiply it by now?
2.
2. So you get 2 on this side. What about on the other side? Well, you multiply it by 2, right? See, like that? So you get 360 divided by pi. So here the pi didn't cancel out. So you actually have to plug it in a calculator. 360 divided by pi. It's about 115 degrees. And that's how you convert radians to degrees when there's no pi. Cool?
Mm-hmm.
It's pretty simple. It's just a conversion factor. Once you know this, you're just multiplying both sides of the equation. That's all there is to it. It doesn't get more complicated than that. Find the length of an arc. So this is an arc length question. So we have a circle. I don't like this software. It doesn't give me an option for a circle. I have to go like all the way down here for a circle, which is so annoying. So anyways, there's a circle and we're asked to find an arc length. So let's say this is our circle. The radius is 12, right? So this is 12 centimeters and it's making an arc. So to make an arc, you need 2 radii. So like this, and the angle here is 30 degrees. The question is asking us, well, what is this arc length here? Arc length is a circumference, is a measure of circumference, is a measure of distance. For us, we're strictly concerned with what's the distance from that point on the circle, this distance, okay, this distance to this point. Cool?
Mm-hmm.
I'm trying to think if there's an easier way to do this. Uh, no, I can't really think of anything. I'm going to teach you the proper way that you're going to learn in grade 12 anyways, and this is it. Your arc length, now this is either denoted by A, sometimes it's denoted by an S, is equal to, doesn't matter what you denote it by, I'm just going to use A, equals L, not L, sorry, R times theta. So A is your arc length, R is your radius, which we here is 12, theta is the angle, the central angle. Now, here's the thing. The central angle has to be in radians, cannot be in degrees. This has to be in radians. If it's in degrees, it doesn't work, which is so weird because even later in life, you'll see that some things you're going to use degrees, some things you're going to use radians. Most things you're going to use radians, but there's still a few formulas where it only works with degrees. And this is one of them where it only works with radians. So to use this, we have to first find what our angle is in radians. Okay, and this is the conversion factor. 180 degree is pi. 1 degree is pi over 180 radians. What about 30 degrees? What do I do on both sides of this equation to get a 30? I have a 1 right now, I need a 30. What do I do?
You multiply by 30.
You multiply it by 30. So if you do it on one side, you have to do it on the other side, right? Like that.
Mm-hmm.
What does this simplify to? How many times does 30 go into 180? 6, right? 6. So that's your angle. So 30 degrees is pi over 6 radians. And for arc length, you have to be in radians. So now finally we can use the formula. Our radius is 12 centimeters. Our theta was pi over 6. So 6 goes into 12 twice. So the answer is 2 pi centimeters. And you can plug that in a calculator if you wanted to. You'll get 6.28 centimeters as the final answer. Cool?
Mm-hmm.
So again, not terribly difficult. Arc length, you just have to know you have to be on radians. All right, let's call it there for today.
Okay, thank you.
Thank you. See ya.